In this video, we're going to talk about the transition elements or the transition metals and their funky D subshell and how we make that the most stable we can. So the first thing we're going to talk about is a couple shifts that occur from what our normal progression is when writing electron configuration for a couple elements. There's a couple principles you have to learn first. Most importantly, that the D subshell is most stable when it has 0, 5, or 10 electrons. When it has any of those situations, they're symmetrical. Okay, they're balanced. There's the same amount in each of those orbitals, and that adds some element of stability to the atom. So the first exception I want to look at is chromium. You can see that chromium ends in D4. So that's very close to being at 5 in its D subshell, which would make it so that they're all uniform and balanced. What chromium actually is capable of doing is taking an electron from what should go in its 4s subshell and then placing it all the way over here in the 3d subshell. And so what it actually has as an electron configuration is 4s1 3d 5. And very similarly to that, copper will do essentially the same thing. Copper ends in D9. It's one electron away from being at D10. So what'll happen is the same deal. It'll shift one from its 4s subshell, and it will end up, instead of being 4s2 3d9, it'll be 4s1 3d10. So those are just the two shifts that you have to worry about with the electron configuration for the transition metals. Now the rest of these we're going to talk about are when they're forming ions. So just to clarify, these are neutral elements I'm talking about making for a stable D subshell. The rest of what I'm going to talk about is the most stable ion configuration that some of these transition metals form. Now, I want to put out the disclaimer that I'm not going to cover all of them, and there's a lot of them get way more complicated than the scope of this class. The D subshell can actually split up into 2 orbitals over 3 or 3 over 2, depending on what they're paired with. But we're going to cover some of the basics in this video. So, the first one I'm going to go to is just scandium. Scandium's most stable ion that it forms, since you can see it's very close to having 0 electrons in its D subshell, is going to be by losing both the 4s and the 3d to form a positive 3 ion. Now, the general rule is transition metals, they're going to lose their valence electrons first. Now, the valence electrons are the highest energy electrons. And when we're looking at this, that just means it has the highest coefficient here, which is the 4th energy level. So it's going to lose those first, and then it could potentially be capable of losing more if it makes for some increased stability. And in this case, if it loses this one, as well as these, it would form a +3 ion and be more stable. Titanium, similarly, was very likely to form a +4 ion, but it can also form +2. If it loses these 2 electrons and just loses the 4s, or valence shell, it would be a +2 ion. If it loses all 4 of those, then it's going to be a +4 ion, being more stable. If we look at, say, vanadium gets ugly. We already talked about chromium as an atom. Manganese gets really ugly. Another one you need to know about is iron. So iron, if it loses these 2 electrons, it's a +2 charge. And this happens. We observe it all the time in nature. It's also capable of losing this additional electron right here and forming a +3 ion. So if it does that, it'll have a nice balanced D subshell. So it can either be +2 or +3 depending on what it pairs with. It'll always lose the valence electrons first, but then you can look at the D subshell and see if there's some way for an increased stability.